record on this computer. Okay, we are recording, and this is our Durwood King with Sampson Community College, and this is October the 15th, 2020, and this class is ELC 111, Intro to Electricity, and we are in our classroom, our shop classroom right now, and we're going to cover Chapter 6 on energy, electrical energy and power, and we're skipping 5 on combination circuits. We're just basically running out of time. We will do the combination series, parallel combination lab. We will do that in the shop, but the chapter would take up so much time that you would end up missing these larger chunks that you've got to have of chapter 6 through 9. You actually get the gist of chapter 5 by doing it in the shop. And I'm just looking at our cutoff date now. Hey, Roger, how you doing? Got Roger joining in. For those of you that are watching, Jamie, howdy, how you doing? Everybody else. Roger is connecting with audio. So let's give Roger a minute to get in. Roger, can you hear me? Can you give me an indication if you can you hear me?
All right, can you hear me now?
Yes, sir.
All right, I had to set it up for a second.
Great. So where are you at? Are you at the beach right now or where?
I'm at the house.
You're at the house, okay. You got a good, you sound clear, so you got a good signal today.
Yeah.
That's great, man. Have you done anything different?
No.
Okay, good. All right, so if you got your book, if you want to flip it up to chapter 6, this is very important. 5 is important too. We'll get you covered. We'll cover that in the shop on your lab. And so anyhow, it's on energy and power. I'm going to flip over to PowerPoint. Okay, so Roger, do you see that PowerPoint there?
Yep.
Great, wonderful. Do you see it in full screen or?
Yeah, I see it. I see. I don't see it in full screen right now.
Yeah, I wonder what happened there. Screen. What do you see on your screen right now, Roger? Do you see like two
different? Yeah, I see it. It looks like 2 different versions of it.
Different versions of it. That's what I want to try to get rid of. Now I got rid of that, but it's not.
Check the options down at the bottom there.
That's what I'm looking for. Wonder why my computer's doing this. Display settings. Duplicate. Hey, how about now?
Yep, that's it.
Full screen now.
Yep.
Is something funky up here?
Yeah, I can't really hear you right this second.
You can't hear me?
I can hear you a little bit. Let me try. All right, try speaking.
Hello?
Yeah, it sounds like you're far away.
Sound like I'm far away? Really?
Yeah, it sounds like you're talking through a phone or something. Is your mic?
Let me check my microphone. But my audio's what? So the audio changed?
Oh, there it goes. Better now.
It's better now?
Yeah.
All right. Wonder why it did that. Anyway, how about now? Did the audio change?
It sounds good now.
Okay. So even though you may be seeing, you can still see a decent sized screen though, right?
Oh yeah.
Let's just roll on with this thing, okay? Yeah, because time is ticking. So chapter 6 is on electrical energy and power. For electrons to flow in a circuit, you got to have a force to move them, and of course that force is, what is that force?
Gotta have a force to move them. That's work, I believe.
Well, if you back up even before work, there we had voltage was a force, right?
Yeah.
Right. So even basic before this, voltage is the basic force that pushes. But we're moving into work because work involves voltage, but it gets a little bit deeper here. Work, okay, energy is the ability to do work. And the unit of work that we use is, here in the US, is called the foot pound. And it's the amount of work that's done when you have 1 pound is lifted vertically 1 foot. It will be called a foot pound. It's the amount of work done when a force of 1 pound acts over 1 foot. Well, maybe even pushing it versus lifting it. If it's dead weight and you're pushing it, a foot pound is still a foot pound. Now, work would equal force times distance. The distance could be a foot, and then the force could be a pound. So, a foot, therefore a foot pound. But work is not really a function of time. It doesn't include a time function in it until you step to the next term, which will be power. So power would be the rate of doing work. So it will be work divided by time. So many foot pounds per minute. And can you still hear me pretty good, Roger?
Yeah, you might want to check your phone. I got a few texts.
A few texts?
Yeah.
From the class?
Yeah.
I don't have anything from a student. Do you? What are you seeing on your phone?
Let me check. I just saw them pop.
I sent y'all two.
Yeah.
I just sent a reminder and then asking, was anybody going to come?
Yeah, one of them said he won't gonna make it, and the other one said they're watching Zoom.
My text is not, but I'm supposed to have Wi-Fi calling. If my Wi-Fi is on. Anyway, we're gonna keep rolling. Advanced calling, Wi-Fi calling. It's on. My Wi-Fi calling is on, but it doesn't always switch over like you want it to. For some reason, it's not ready 100%. Okay, so and everybody really can go back and watch. I'm recording. I'll upload this to YouTube after, so whoever misses can go back and watch the recording. That's the beauty of that. So anyway, so power would be the rate of doing work in foot pounds per minute. That's 1 unit of power. There's all kinds of ways of looking at power. It can be expressed in foot pounds per minute. Now, when you also look at a commonly used unit of power would be a horsepower. And you can Google and look that up, and the origins of it really does come from way back whenever someone defined a horsepower. They said that an actual horse, a common horse way back a long time ago, could pull 33,000 foot-pounds in a minute, and they called that a horsepower. For real, it actually did come from a horse. So it really did come from a natural horse, that could do that. And y'all see them plowing in the field, they can do a lot of work. So anyway, so 1 horsepower would equal 33,000 foot-pounds per minute. So that horse could drag that much per minute. Now, power can also be expressed in wattage, like a 1,000 watt, or 100 watt bulb, whatever, 40 watt bulb. So the watt or the kilowatt is used as a unit of electrical power, and it can be measured with a dedicated meter called a watt meter. And the watt meter is shown on that slide there. It has 4 terminals to it, and it has a movable coil in the center with a needle, and then a fixed coil or magnetic field around it. And you connect the voltage of a circuit to one with the load, and then you have the current coil is, all 4 of those would connect to a meter, and or to a circuit. This would be the actual meter itself. That's the internal parts of a older style analog watt meter. So the voltage in the circuit will be connected there, and your power source, current coil. They're not showing how they hook that to a load, and I'm just thinking here how to explain how you would connect it to a load.
Do you have to disconnect the circuit and put it in there?
You would have to disconnect the circuit and put it in line. That would be a physical inline coil connection for current for amps.
Mm-hmm.
So it would have to go in line with the circuit. Like you said, you would have to break the circuit and put that current coil in line between your load. But here, I found one of these in the shop, and I've never had a need to use it, but I'm going to just show you this one. I'm going to hit stop screen share and go back to camera. Now, so do you see?
Mm-hmm.
See that, Roger? So that's actually a watt meter. And at the bottom, it has your power source hooks to the outside terminals, and then your load would connect to the center tube on this particular one. And
Gotcha.
Anyway, I've never had a need to do that. I've never used this. As an older one I just found out in the shop that's been sitting out there a long time. So that's just an example. If you were doing the power measurements, that's just an example of it. It's not something that would be commonly a need of, unless you were doing some probably engineering level measurements on circuits. That then you would need it.
Gotcha.
Let's go back there. Now, so are you back to full screen now?
Yep.
We're
Or
pretty
close
close
to it. Yeah, close to it.
Yeah, doing pretty good. I got a Zoom class going on. How you doing? She's hanging in there. She working with the therapy doing. She's slow to getting better. Okay, good to see you. I saw you gonna teach MNT 111 next semester. That's good. They're gonna get you up here next semester to teach MNT 111 maintenance procedures. That's good. Good. All right, man. He's a really good welding instructor. He's a veteran for sure. Okay, now so so y'all have already been calculating wattage on one of your worksheets on that advanced Ohm's Law worksheet, and you have 1 watt in a circuit. If you have 1 amp flowing and 1 volt, that would be 1 watt, because the amps times the volts equals the watts. If you have 1,000 watts, you can shorten it to kilowatts. So 1,000 would be K for kilo. So kilowatts would be 1,000 watts. Now here for
Yeah.
calculating power, there are three power formulas that they show here, and these are, they're derived from the pie chart. So if you look at the one that says P equals I times E, then that P, if you go into the pie chart, the upper left corner of that pie chart there,
Come on, boy.
then P would equal, do you see my mouse moving around, Roger?
Um,
The mouse or not? I see it
Come on,
on my
Copper.
screen, but I don't see it up there.
try moving around to the center of the screen because I don't see it. Yeah, I don't see it. Oh, now I see it.
Now I've got it fixed, and I hit duplicate slideshow, now everything's it's perfect now.
Gotcha.
So great. Okay, I knew there was a way to do this, but there's just a lot of settings in here.
I was wondering why you're still on that same screen.
Right, I hadn't hit duplicate. I had to go under screen presenter options, and anyway I found it. So yeah. My brain this time of the week, I need a fish plate, Roger. That's kind of what's wrong here. My brain's not moving quite as fast.
Well, there's a good fish place that's been done.
Yeah, we got one here, a couple in town. We got Sandpiper and actually three: Sandpiper, Carolina Fish Fry, and Southern Style. Southern Style I had last week, and they give me a really big, nice, small plate. We had three big pieces on there, man. It was good.
Yeah, but in Dunn, there's a place called Seafood Express, and you can get the seafood platter.
Yeah, that's it.
And they give you everything like fish, shrimp, fries, oysters, hush puppies.
I will say, though, it's probably going to be, you might want to call 20, 30 minutes ahead of time.
Yeah, but it's only like $13.
That's good, though.
Seafood Express.
Yeah, it's like a little shack. You like if you don't know where it's at, you're gonna miss it.
Yeah.
I remember that if over that far.
You sound. Can you hear him, Brandon?
Yeah, I can hear him a little bit.
Yeah, it sounds off again.
Sounds off again.
No,
Yeah.
you're just far away from the mic.
Yeah.
So hold on.
Yeah, that's probably.
See what's going on here.
Or maybe it's your volume on the computer.
Can you try talking into the mic?
How about now?
Nope.
Let me reset. How about now?
Nope.
Let me switch.
You might be able to go to the settings and turn up your mic a little bit.
Now, it's changing which mic I'm using.
That's better.
Now I'm going. Okay, now I'm on the. I went right back to the computer.
Yeah, that's better right there.
That's better.
Yeah.
Something
Yeah,
happened whenever I changed the video. That it's doing something with the. So, did the audio change then?
Yeah.
Yeah.
Huh?
But see, it didn't change. It didn't change. It just like muted for a second. But I think that's because
Do you still hear me well now?
Yeah.
it's like your computer processing.
It sounds good, Darwood.
I was changing. I was trying to get the video set back up again. So now, if you look up here, now why have I got that set? Now, let's move that down, that bar moves. Okay, so P, power in watts equals I times E equals current times volts. So that P equals I times E comes from up here. P equals I times E. That's the center formula in that quarter of the pie chart. The other one that says P equals voltage squared over resistance, it also comes out of the pie chart. So that one is right here. P equals E squared over R, volts squared over resistance. Everybody see that? My mouse moving around?
Oh, yeah.
So that's your second one out of the pie chart. The third one is power is going to be equal to current squared times resistance. So P also equals current squared times resistance. So you've got three options to solve for power depending on which two variables that you're given in a problem or a situation. So if you know what the amps is and the resistance, you can get power. if you know what the volts and the amps is, you can also calculate it and get the same number too, by the way. If you know what the volts is and the resistance, and you don't know what the current is, then you can say volts squared over resistance. It's going to give you that same number. So all of them are going to agree to the same wattage.
In other words, if you have any of the other two factors, you can figure out the third one.
Yes, exactly. So the pie chart, the reason why you need that pie chart on you, and the little cards I had, the little business cards I had that I had give out on the flip side, it's got all of this on there. And so no matter what you're solving for, if you're solving for amps, for I, there's three ways to get it, depending on which two variables that you have. And same thing for voltage. If you're solving for volts, there's three ways to find it, depending on which variables you have. So you can really solve for what you want to solve for with all 12 of these formulas.
Gotcha.
And the triangles are actually derived from the pie chart. You have three formulas in here and three in this one. And this is like, your training wheels, you learn off of this, and then you really want to stay with this, because this has everything in there. This gives you the whole scope of what you can use for Ohm's law. Everybody cool with that?
Yep.
Great. Let's make sure I'm still recording here too. I want to make sure we are. I'm just double checking. You don't never know with this is a delicate. This stuff is delicate technology. It's great, but it is kind of delicate.
Yeah. Anytime you got technology that's smarter than the last, it's usually really delicate to like the minor details.
It is. It's very delicate.
It switched to microphone.
It switched again.
Yep. Have you got something with a microphone connected?
I do, but in the settings right there, if you look, I'm still on the computer mic. But if I switch to my mic on the webcam and then switch back, it seems to fix it. So is it loud now?
Yeah, it sounds good.
All right. I don't know what that is. There's something's happened by me interfacing with this smart board in here. I got my laptop going into the smart board, so there's something a little going on. Anyway, we'll work through it. Okay.
One thing you could do is buy like a headphone with a microphone on it. That might.
Yeah, I've got that. I've got one of those, but it's very restrictive.
Oh, okay.
The link to the cord, I can't walk over here to the board. I can't move around, so I started out using them months ago, and then I got away from it because the mic in the computer is actually just fine.
Or you could probably get like one of those Bluetooth pieces and try to sync it to the, I don't know if it'll sync to the laptop.
That's a thought there. It is. Yeah, that would probably be fine there.
Well, the pair of earbuds I got that I'm using right now, there's some that are just about like it that cost like $35, and they pick up just as good.
Okay. Maybe I can look at what you got, Roger, when you bring them in and just kind of see. There's a lot of them out there,
Oh yeah.
Now, so our next thing would be here for power. Energy consumed is measured in watt hours. How many watts do you consume in an hour? That's what you're actually paying for on your electric bill. So 1 watt hour would be if you use 1 watt for 1 hour. And then 1 kilowatt hour would be if you use 1,000 watts in an hour. That's like saying if I had 10 light bulbs that were 100 watts a piece, and I burned those 10 bulbs for 1 hour, that is 1 kilowatt. And that's the basis for your electric bill. My electric bill coming from South River Electric, I pay 11 cents per kilowatt hour. if you calculate on your electric bill and you look at how many kilowatt hours you use, and you do the math between your total bill and the number of kilowatt hours used, it's going to come down to somewhere probably around 11 cents. If you deduct, if you have security lights that you're paying lease on in your yard or anything like that, I got like 3 of them in my yard. You take that off and just look at the basic bill after that with the number of kilowatt hours that come off of your meter base just out behind your house that shows. Matter of fact, if you've never done it, go to your meter base outside, and it's going to give you a digital reading of how many kilowatt hours you're using in real time. So it keeps running total of it as you go through the month, and that meter is called a smart meter. If you look in our book in the ELC 113, our residential book, there's a section in there on smart meters, and those meters they actually send a signal out to the power company remotely each month that tells the power company how many kilowatt hours you've used. Now, a lot of years ago, they had what they call a meter reader.
Yeah.
A person that came into your yard, and they had to go to your house and read it on a analog display. And you had issues like dogs trying to bite them and people get mad and all this kind of, and then fences to where you couldn't get to it. So there's all kind of problems with a meter reader, and they got away from it stuff. So everything is remote now. So it transmits from your house to them, and then they bill you. So your electric bill is for how much energy that you use, not power. So what do we mean by that? They're not billing you for how many watts that you use. They're billing you for how many watts per hour. It's actually a rate, so the energy is measured in, you're paying for kilowatt hours. And then they actually charge you, the basic unit would be X amount of cents, so many cents for a kilowatt hour. Now for South River Electric, it's about 11 cents. So Duke Energy, I'm not sure. Do you know what yours is at home? Or the next time y'all get your light bill, take a look at it and do a figure on it and see what it's what they're charging you. It's probably going to be around 11 cents roughly.
Yeah, ours is South River.
Yeah. And
I do not know.
All right, so now let's see. Let's go. Before we go to this part, let's do a calculation that's in the book on kilowatt hours. The slide does not show that. The slide goes right on to converting from wattage over to horsepower. Now, so I'm going to cut the webcam. I'm going to switch over to webcam. We're going to do something on the board now. So I'm going to stop screen share, and we're going to go here. And let's go. So, are you getting the full screen now, guys?
Yeah, you.
Yeah.
You getting full screen now? I'm actually seeing you more than I am me, but that's fine. There's supposed to be a way of getting
The 3 little dots at the top. Hit that and pin video.
Thank you. I appreciate that, man. That was cool, Roger. Thank you.
Yeah.
You're teaching an old dog a new trick. Okay, how about that? Yep. Now let's rotate this thing around. Yeah. I love this camera, man. This little gooseneck camera, it is the coolest thing, man. It really is. So but when I get over there, you tell me if you can still hear me okay or not. Okay, so on page 47, they're saying that the cost would equal how many watts that you have times the hours used. The dollars per kilowatt hour. Per kilowatt hour. By 1,000. And that'll give you the cost. You all sit down on the board pretty good?
Yeah.
There you go, great. Great, this. Let's have an example here of a television set. This is a good little thing if you want to know how much it costs you to run a TV, not to leave it running when you're not using it. Is if you have a television that runs for 6 hours, it's 150 watts. You get that wattage off of the nameplate of your television or your refrigerator. And the cost of energy in this case is 5 cents per kilowatt hour, which has been a lot of years ago. Okay. So we're taking.
What's that TV?
So we're taking here the wattage of 150 watts times the 6 hours. And then the amount of how much is it? So you would express it in dollars, which would be 0.0 if it's 5 cents per kilowatt, $0.05. So you need to express it in dollars when you do this. Instead of saying 5 and then a cent sign. So 150 times 6 hours times 5 cents divided by 1,000, and it ends up being, the answer ends up being
450 divided by 1,000.
it would be $0.045. Now, if you convert that, and it's 4.5 cents. So 4.5 cents is what it costs to run that television. But you're talking about a lot of years ago. Now, what would it cost now? Seriously, if you do it nowadays, it would be 11 cents on my bill. So let's calculate that. Let's just see what would it be nowadays. Let me do a little roll call here while I'm at it.
Present.
That damn beetle scared the fuck out of me.
A beetle?
Yeah, he comes straight from my face. I was like, oh shit.
That happened to me the other night. I was like, I'm sleeping on the couch. I was trying to get a look at the nameplate on my TV, but it's behind a bunch of stuff.
Hold on, I could probably see mine.
Because I figure it's probably changed over the years.
Let's see. Mine's 110 watts.
110 watts, right?
Yeah. But it's only like a little 32 inch though.
Uh-huh. Yeah.
Don't worry, mine ain't any bigger.
So, what did you come up with there for the 11 cents?
9.9 cents.
9.9 cents. 9.9. 6 hours. That's what you're paying. You're paying about a dime for 6 hours running. Again, it's 11 cents if you use 1,000 watts for an hour. But you're only talking a percentage of it, 150 watts, not even close to 1,000. So it's going to be, that's what you end up with there. Okay? Everybody cool with that?
Yeah.
Okay. There on your worksheet that I've got in Moodle now, I put it in there last night. There is an example. Number 8 shows an alarm clock that it uses 2 watts of power. So the example on your worksheet would be number 8 when you get in modal, and it says determine the cost of operating a 2-watt electric clock 365 days, which would be a whole year, at 11 cents per kilowatt hour. Now, here's what you want to do in that. For the 365 days, what do we do with that for our calculation to get the hours?
You take the cost. No. Okay.
365 times 24.
Exactly. So to include that in there, you want to convert days to hours. And that's, and then you'll plug those numbers into this, and then that's going to get you what you need.
But being that there's an extra 2.25 days on the year, do you add that to, or just do 365?
Just as it's saying right there, the 365. Okay. Just take it literally, as it says. And what did you just say about what now?
You know how like every 4 years there's an extra day, so really every year has like 0.25 days.
We don't count down the calendar, so.
Or like just round it over or something.
You talking about leap year? No.
Yeah,
leap.
like.
So is leap year the one where you have where February is 1 day shorter?
1 day longer.
1 day longer, yeah, 1 day longer. 29 days versus 28 days, is that what it is?
Yeah.
It's February that has that change, yeah, for some reason.
Yeah.
Just stick with 365, yeah.
Okay.
Okay, now, everybody cool so far?
Yep.
Great, moving right along.
Would it be 1.2 or 1.9272? Or
yes, and if you round it in dollars,
be $1.93.
Absolutely, yes, sir. So that's number 8 on your worksheet. Yeah, it is. It sure is. Yeah, that's a big 10-4.
Did you already give us the worksheet, or is this one in Moodle?
It's in Moodle.
Okay.
Yeah, it's in Moodle. Yeah. It's a brand new one in there, and it's good to jump on and get it done. Next week we're going to cover chapter 7, and then 8, and then 9. Semester's going to be done in less than a month. That's including the exam. So now the next thing is, and if you don't have any questions, we're going to move on now to power. An electric motor converts electrical power to mechanical power. So ideally, 746 watts equals a horsepower. So that's an important factor that you're going to need to do some calculations on the worksheet. Is that conversion there? 746 watts equals a horsepower, and it's in the book. Shows that on page 48. Now, with motors, they're never 100% efficient. The power that you deliver, that you supply to them, does that you don't get 100% of that out of the motor, so you lose a little bit because of internal resistance in the motor, friction. So you have some heat losses in there that make it less than 100% efficient.
But wouldn't this be ideal or whatever?
Say that again.
Wouldn't this be like ideal output or something when you don't include losses?
Well, we're going to include losses in these calculations. We're going to say that in reality that you have X amount of power going to the motor, but then you actually end up getting X amount of work out of it, and then you're going to calculate the efficiency based on the losses.
Okay.
Okay, so efficiency would be measured. Do y'all see the screen there, the formula?
Yes, sir.
Okay, so the efficiency is calculated by saying how much output power do you have divided by the input power. That'll be a percent, or a portion, a fraction of it, times 100. And that's going to give you the times 100 puts it in a percent. Okay.
All right.
So with that, And then also they've got another example there on the bottom of 48, calculating the cost of running a lamp for 24 hours. I don't think we particularly need to do that because it's the same repeat of what we just actually. We actually do need to do it because it involves a calculation you need to look at. So let's see.
And this one on the worksheet too.
Hold on, give me just a second. We're getting ready to do this anyway. Okay, so the efficiency is used. It's included in the worksheet on number 5. And we can actually do that together because they're not giving you an efficiency example here in the book. So let's go ahead and do that one together. Yeah, let's just do it together because the PowerPoint doesn't include everything.
What page is it on?
It's on the example for efficiency. They don't do an example. It's actually in the worksheet. So let's do, and like in the review at the end of the chapter, it's in there. It's in there, but we're going to do it together. It's in the worksheet I put you in Moodle. But it's number 5 in your review at the end of the chapter. It's number 5. But let's do that together.
Okay.
So let's get this over here. Yeah, this is important to do this together. Especially for folks that are watching this and can't talk back right now. They're watching the video, Jamie and different ones. So number 5 on your worksheet is we want the overall efficiency of a motor that delivers 2 horsepower to a load if it draws 7.5 amps when connected to a 240 volt supply. So let's draw a power source here of 240 volts, and we've got a motor here. It delivers 2 horsepower, and it's drawing 7.5 amps. 7.5 amps flows, there's 240 volt supply, and it's delivering 2 horse out there to the motor. And so we want to figure the efficiency. Now, efficiency requires that
we find the resistance.
It's going to be output power over input power times 100. But these units have to be the same. Now, we know that input power is 2 horsepower. Input power can be calculated using the volts and amps. It ought to give you watts, but you're dealing with wattage and horsepower, and you've got to have apples to apples. You have to have either watts and watts or horsepower and horsepower. So you got to convert either this to watts or convert this to horsepower, and then you can do it in efficiency calculation. So if you want to flip it over to watts, we can do that because we haven't done that yet. So what's our conversion factor for wattage to horsepower? If you look on John,
746.
Exactly, 746 horsepower. 746 watts equals 1 horsepower. So how can we convert 2 horsepower to watts?
7.
You say 2 horsepower times 746, right? Because 746 watts equals 1 horsepower. We're talking 2. We're just going to double that, right?
Yeah.
Yeah. If
Because there's 2 horsepower.
746 watts, 2 horsepower is just going to simply be double that. Okay, so what would that be?
Yeah.
42. Is that? I can't see the number.
1,492 watts. Everybody agree with that?
Yep.
Yep.
Y'all see that okay on the screen? Yeah.
Yeah.
This is working out nice. Thank Lord, that's good. Okay, good. So now you got now you can compare apples to apples. So which one of these is output power? Which number goes on top?
That one right there. Yeah, 1,400.
Look, you got the wattage here, but we don't have the other one. How about the is this output power or input power?
Output.
It is output power. So it's going to be the 1,492 watts on top. Now input power, we got to have it in watts, right?
Yeah, and it's going to be your volts times amps.
Exactly. Very good. Thank you. So if you multiply the 240 times 7.5 amps, then what does that equal?
I'm scared to go to my calculator on my phone because I'm scared it might exit me out.
You said 2.75 amps.
Going in here, 1,800. It's the even 1,800 watts. So your input power, it's actually putting out 1,800. This power supply is actually pushing out 1,800 watts. And guess what? You're actually paying for 1,800 watts to the power company. You're paying for that. Whether you're getting it at the motor or not, you're really not getting it all, but you're paying for it. Some of that's lost in heat, friction. You just have some. You always have some losses there. So you do this division here, and then you say times 100, and that's going to give us a percent, which would be what?
It would be like 34%, something like that. I ain't got a calculator on me, so I can't really do it.
I can't exactly see the board.
It's 1,492 divided by 1,800 times 100.
And let me see if I can maybe focus this better.
Yeah, wait, go back a little bit. Yeah, right there.
Right there?
Yep.
88, 82.88888. So it's basically 83. Oh, right there.
Yeah, right there.
Okay, good.
So 83.
You can say 83.5. You got it's 82.9, 83.5. And you put the percent sign there.
Mm-hmm.
So if you leave it, if you don't multiply times 100, it's going to say 0.83. Okay. Everybody cool?
Yep.
Yep.
Okay, great. Any questions?
Nope. Pretty good.
Very good. Now, so next thing was flip on to let's go back to okay. Do you see my screen again?
Yeah.
Okay, great. Here. Now we have a sample problem in the book. It's at the bottom of 48 and top of 49. So here they're saying, I'm actually going to draw. I'm going to go back over to the camera because that way I can actually draw. If I try to draw on that, it's not really going to reflect that. So you can draw on the smart board, but it's not going to be equivalent right here. So stop that. Let's go to video. Now we're back to that. So I just going to go old school over here. And we have a lamp. This is what I'm used to back, for the last 10 years of doing it this way. Resistor in line. And our power source is 45 volts. And we have a resistor R1 of 7 ohms. And a lamp that is 2 ohms. And so it says we want to calculate, first of all, the power delivered to the lamp. So we want to know the wattage that the lamp is consuming. That's our first question. How do we arrive at that?
Hold on. I'm trying to pin your video back up so I can see it. Because I'm stuck right now.
Step out of my car and grab my calculator real quick.
Okay. Yep, let me grab a swig of water.
Are we finding the total watts or just for the lamp?
Well, the first question is going to be just for the lamp.
Okay.
And then it's going to want to know the cost of operating the lamp for 24 hours at 4 cents per kilowatt hour. So everything's going to be based on the lamp,
Okay.
That 5 cents, that's way back, but just go ahead and stick with it because it doesn't matter what the cost is. You can plug the current numbers in there, for what you're doing at home.
Okay.
Well, I tell you, we've had to get creative this year. I ain't kidding. This has been a different kind of year. If you told me in December what this year is going to be like, I'd have said, "Is you for real?" I said, "Really?" I said, "No, really." Yeah.
Oh,
About no Corona, nothing. I'd say, "Corona who?"
yeah.
January, you started hearing about it, and I remember thinking, yeah, that's just something over in another land somewhere, another country. You think about that. Just like other things you hear about, you don't think about it ever hitting the U.S. But
What's up, Mama? Oh, you did?
I've never seen.
I forgot to take the trash can to the road.
Never. I mean, I'm 57 years old. I've never seen anything affect the whole world. Nothing.
All right, I'm back. What did I miss?
Okay, so you got your calculator now.
Yep.
Yeah.
Okay, so how do we go about doing this?
45 squared divided by 2.
Now, okay, so he's using the Ohm's law. D squared over R.
Yep.
D squared over R. Okay.
And I got 1,012.5.
You can't use 45 volts over there because you don't have 45 volt drop across.
Oh, okay.
45 across the resistor and that, so you can't use that number directly. I mean, that's a good formula, but the voltage you put in there is not what you would read across that, because what kind of circuit is this?
It's in a series.
It's series, yeah, series. So if you're going to use E squared over R, you've got to know what is E. Okay, which is going to be another thing to throw in there before we do that. So you can do that if you want. It's actually going to take you an extra step. What's another formula you can use?
Figure out the volts across each resistor and add them together, or figure out the amps first.
That's what I would say. I would say get the amps first. Get your amps first, and then you can use one that's involving amps and resistance.
Yeah. So then that would be E divided by R, so 45 divided by the resistance. So
Yeah.
45 divided by 9.
We want I total, right?
Yeah.
So it's going to be E total over R1.
Total.
R total. Total is 45 volts, and R total is
9.
yes, 9. Okay, so what is I total?
5.
5 amps, exactly. So now you can use the current, because you know it's the same throughout both loads there. The current and the resistance. Which one you can use now?
The voltage times the amps. So 45 times 5.
Well, look, the 45 times the 5 is E total times I total. It's going to give you total wattage for the whole circuit.
Oh, the whole circuit. Okay.
Because look, the 5 amps is I total, right?
Yeah.
It actually flows through the whole thing. The 45 volts is distributed between these two, so neither one of them gets 45 volts. If you say 45 times 5, it's going to give you the total wattage of both of the resistor and the lamp together. Total power consumption for the whole circuit.
Okay.
The resistance of each piece.
Right. So you can use the current and then the individual resistance to calculate wattage by using which formula?
The
Well, it's I what?
Total resistance.
You can do something to I. Go back in your Ohm's law pie chart and see what does it say.
I decided
P equals I times E.
Well, P. How do you find P if you have I and R?
Oh, wait.
I squared times R.
Times R is going to equal P, right? So it's going to be the 5 amps squared times the resistance of the lamp itself on 2 ohms, and that'll give you the wattage of
50. 50.
50 watts. Exactly. So the current is the same for both, and you're going to square it times the individual load resistance of this one. Because you want power consumption of this one, not that one. They're using the resistor to actually drop voltage and reduce current, but they're using it for a particular special bulb there. You'll see series resistors used with LEDs. If you have little LEDs on equipment, LEDs don't really burn on their own. They have to be, the voltage source most of the time has to be reduced with some series resistor for LEDs.
Mm-hmm.
That's typical for LEDs there. Anyway, so that will be the power consumption for the lamp. And then they want, for question B, they want to know what's the cost of operating that lamp for 24 hours if it's 4 cents per kilowatt hour. So let's just go back up here and say that we've got 50 watts, right? Then we're going to get rid of all this. Everybody got that? I'll stand out of the way so whoever's watching recorded can see. there for a minute? How we arrived at all that?
48.
So now, what is the formula for efficiency? How do I figure efficiency? What's on top? What's on top and what's on bottom? I mean cost. What am I saying? It's cost. Cost. What's the formula for cost?
1 times hours. Probably kilowatt hour. Over 1,000.
Time. Dollars.
Sorry, somebody was calling my phone. So.
Divided by 1,000.
Oh, that's what I forgot.
Okay, so we have our wattage. We know what that is, right?
So that's 5 cents.
Yeah. Yeah, 50.
The hours would be 24 hours.
24.
And then the price per kilowatt hour is 4 cents. We need to express that in dollars, okay?
Uh-huh.
Dollar sign and then the 0 and 0.04, right? Would be 4 cents.
Yep.
Per
Yes, sir.
kilowatt hour, and then you get all of that and you divide by 1,000. And then what does it come out to?
About 5 cents.
48. 4.8 cents.
You keep it exact there. So,
Okay, I did. I figured you'd, I got you.
$0.048. And if you move it over the decimal 2 places, it converts it to cents, which would be 4.8 cents. So keep everybody watching the video, keep it exact. Don't round it. Just keep it exact. It will come out to be three decimal places, but when you move it over, if you express it in dollars, make sure you include all the digits. And if you do it in cents, make sure you move the decimal over 2 places and change the dollar sign to cent, because it's easy to get mixed up and say $4.8, and that wouldn't be right. Well, that's the wrong answer. If you put a dollar sign out here, then that's going to be wrong, isn't it? It's not $4.8. It's 4.8 cents, or it is $0.048. So y'all watch closely on that. You put the answer right there. It's difficult for that to happen. I see it every year. I see that happen with somebody, but.
Yeah.
Okay, now next, we're moving along very good. Appreciate y'all, your participation. This way, everybody out there in Zoom land's not going to get bored just looking at me, right? They're hearing you, so that keeps them awake, right?
Come on, Durwood, you're real exciting.
Yeah.
I appreciate it. Thank you very much. Thank you very much.
Thank you very much.
Thank you very much.
Mhm.
Okay, let's go.
How?
Let's go to share. Okay, y'all see my screen again?
Yes, sir.
Yep.
Okay, so now we have, let's see. Then it gets into the review questions. So let's look at what have we not covered? Let's make sure that we. Why don't we do a really large one together?
Yeah.
Sounds fun.
A really large one, and this will be number three in your worksheet. It's a big one.
Really? Number 3. The motor, let's lift it. Elevator cart weighing 2,000 pounds, height to 1,000 feet in 4 minutes.
At a constant speed, what horsepower rating is required of the motor? Okay.
Oh, got it.
Just give me, go ahead and do this because this one that we kind of get, it's hard to learn how to work through the whole thing if you're on your own. Let's suppose that we have an elevator. I'm going to draw an elevator shaft here. And I've got the second floor, first floor, second floor.
So power or
like a winch with your motor, got a motor up here that's going to be drawing the elevator up and down.
so force would be that'd be watts. Am I correct? Or
No, four would be the time.
force would be,
Minutes.
and then distance would be the height.
Foot pounds per minute. I think that would be the feet. No, that'd be the 2,000. And then work done would be the feet, right?
Yeah, work done, I believe it'd be feet. So it'd be 1,000 divided by 4 minutes.
So 1,000
Be 250.
in 4 minutes.
Right.
It has to get all the way, say maybe to the first and the third floor and in 4 minutes, which that would be a mighty slow elevator in the hospital. People be going nuts over that. So
Yeah.
if he beating on it, you know. So okay, so at constant speed. So the question would be now would be, what is the horsepower of the motor? What is the horsepower of the motor? What's required? If you went out to order a motor, they calculate this stuff at Schindler. They have escalators, and then they also make elevators at another location. But anybody working at Schindler this would be interesting for that person. So when your first step, if you look, if you want to calculate, in order to get 2 horsepower, to get to that point, you've got to have foot pounds per minute, right? Foot pounds per minute, and then you can convert foot pounds per minute over to horsepower. So
Would it be?
So your first step, I think, is going to be you got to get a foot pound calculation first, right?
And I believe that would be like the 2,000 times the 1,000, right? The force times the distance.
Yes. So the force would be the 2,000 pounds and times the 1,000 feet.
And I believe you get 2 million.
And then you divide that by 4 minutes, right?
What kind of unit, when we say it's 2 million, it's 2 million what?
2 million, that's to work.
Foot pounds.
Oh yeah, foot pounds.
It's important that we know what unit that we're looking at. And so we have 2 million foot pounds, and we're looking at the amount of time when we want to convert that over over the work, then we got to have, foot pounds per minute, right? So
Yeah. I believe you get
Divided by 4.
500,000. All right. I wouldn't say this 500,000.
Yeah, 500,000.
And then after that, I think you convert it to horsepower.
yes. Okay.
Divided by 33,000.
So what's the answer here when you divide that out?
15.15.
No, 500,000.
500.
Oh yeah, that one.
Yeah, and then you divide that by 33,000.
It's 500,000 more.
It's
Foot pounds a
5,000.
minute.
Yeah.
Foot pounds per minute.
Foot pounds per minute. 500,000 foot pounds per minute.
Mm-hmm.
So you want to have that would be your unit description for that number. It's 500,000 foot pounds per minute. When you divide that by 4, then you break it on down to per minute. You break it. Okay, and now, so what's your equivalent, what's your conversion factor to go foot pounds per minute over to horsepower?
Divided by 33,000.
Right. We know that 1 horsepower
Equals, yeah, equals that 33,000.
foot pounds per minute. One horsepower, 33,000 foot pounds per minute. So if we simply divide this, if we divide that and put 33,000 under that, and divide those numbers, it's going to do a direct conversion in the horsepower, right? Which would be how much?
15.15.15 repeating.
15.15 horsepower. So the engineers at Schindler that make, or Otis that make the escalators, or the elevators, this is the engineering level calculation that whenever they go to buy a motor, order a motor for that escalator, they or that elevator, they have to have at least a 15 horse, and I would probably go up higher than that. That
Oh,
would
don't
Do like 16.
well, don't they
they go in probably increments of like 15 to 20.
Okay.
Odd increments of horsepower.
Well, I got a question.
You can definitely go up the horsepower above it. It's fine to do. It's fine to do. You don't want to cut it too close. You don't
So this are so this.
it wouldn't be the last, but it wouldn't, the life cycle it probably wouldn't be too good.
Hey Durwood, I want to let you know the mic's or my Bluetooth headset's probably gonna die soon.
Your Bluetooth what now?
My microphone's gonna die in a little bit. I just heard the little sound.
The battery. The battery.
Yeah.
Yeah. Okay.
Yeah.
All right.
There's an option if you go to let's see, what was it?
Can you switch back over to computer?
Oh yeah, I mean, I was just saying I wouldn't be able to speak.
If you do it on your phone, you can like it'll let you talk through your phone. You just gotta do like talk through call or something like that.
I might have a spare Bluetooth headset I could use, but I mean, I could just listen.
Yeah, you could do that.
What are you using to view this on? Are you on a computer?
Yeah, it doesn't have a microphone.
It don't have a mic. Okay.
No.
But you can call in, you can dial in, right? With a phone?
I can just use the other microphone I got laying around.
Okay. There you go. That'll work. Okay, so everybody cool with that example there?
Yes, sir.
Yeah.
Okay, good. I'll make sure that we cover each type of a problem here. All right. We have another one that would be a good one to do. Number four on the worksheet.
Oh, that was the actual. I forgot that was the actual problem that we need to solve.
Yeah, your Bluetooth what now?
My microphone's gonna die in a little bit. I just heard the little sound.
The battery. The battery. Yeah. Okay.
Oh, yeah.
Mm-mm.
Standing
Type
out
that
there,
into the
you need to see
worksheet.
this on the video. There it is. You can just hit pause.
No, I got it in my calculator. I had to go back through the history.
Yeah, this board here was like before Corona. That's when I was using these. Okay, so now we have number 4 says find the cost of operating 10 100-watt lamps at their rated voltage for 11 hours at a rate of 10 cents per kilowatt hour. So here's what I recommend doing on word problems. If you draw the circuit out, it's going to be a lot easier. That goes for, I don't care what kind of all electrical problems. If they're in a word form, go ahead and draw a circuit. To draw that circuit out, don't try to manually do this because it's just too easy to make a mistake, you know.
Yeah.
Or it'll take you longer, like I do.
Yeah. So we're going to say we've got 10 bulbs here. 2.
Is this going to be one of the problems in the worksheet?
It is.
Which problem is it?
This is number 4.
Number 4.
Okay.
We got lamps here, 10 of them. Three, four, 5, 6, 7, 8, 9, 10. And they're 100 piece. 100 watts.
Well, I'm attending one of my classes online right now.
And we're gonna run these bulbs for 11 hours.
Must be a hotel room with that many lamps.
Nah, probably a warehouse
Yeah,
or something. Or yeah, something like that.
a store that sells lamps on the showroom floor, I guess.
It's all the displays.
Okay, so how do we do this? We're looking for cost.
So that would be the total watts times the hours times the rate per hour, right?
So would watts
Divided by
be times?
1,000.
So would you times the watts by 10 because there's 10 lights?
Right. So this is what gets people in the rear. People will do this and they'll just count 100 watts. So your first thing would be to figure this. You said the word, I like the word total. You said total, that's correct. Total watts would be what?
1,000
Right. And you got it by doing what?
times in 100 watts times 10.
100
Yeah.
watts times 10 volts. And that equals 1,000 watts. So that's if you count 100, then it's wrong. Okay.
Yeah.
So now the cost would be, we said total 1,000 watts. Thousand watts times
11 hours.
11 hours. And then
Times 10 cents per hour.
and we want to express that in dollars, don't we?
Yes.
So it would be 0.10 to give you the right way of putting it in there.
Divided by 1,000.
Exactly.
And I think it's 1.1 or something like that.
Right. 1.1 would be $1.10.
Yeah.
You want to put the zero in there. You put it in terms of dollars. I mean, to have, when you don't, if you leave the decimal as it is, it's actually in dollars, so it's $1.10. So this is a good clear example that you can see that you really have 1,000 watts there. You're paying for a kilowatt hour is 1,000 watts that you use in an hour. So that's like I was saying earlier. 10 light bulbs that are 1,000 watt, that are 100 watts a piece equals 1 kilowatt, 1,000 watts. And that, in other words, if you tell me off the top of your head, what would it cost to burn them for 10 hours? 10 hours.
Let's see. Move that over one, so that'd be $1. $1 divided by 1,000. So it'd be like
Hello? Can you hear me?
1,000th of a dollar,
No.
or 1 cent,
Just put
something
10
like that.
here. 10 for 11 hours. It's this. Put 10 in here. What is it for 10 hours? It'll be a little.
Oh,
less.
$1.
It'll be $1 even. Yeah.
Hey, Brandon, can you hear me?
Yeah. Yeah, I can hear you.
Okay, I had to switch over.
So that, and actually, my power bill really is like 11 cents. So you look at some real numbers here. So it's important. It's a good thing not to leave lights on at home, man, because somebody's going to pay for it. You're paying for it. Folks are paying for it. Somebody's paying for that. And that's why the occupant sensors are really great to have those in your rooms. You can put an occupant sensor in the place of a wall switch, and you can set a timer on there. And when you leave, that timer says, if you set it on, whatever, for a minute, it stays on for a minute. If there's no activity, it's going to cut off.
I went over to a lady's house to pick up some stuff the other day, and she had one of those for her hot water heater and mess. That cut on at certain times and cut off at certain times.
That's right. She had a cycle timer on there that she could say certain times of the day it will come on.
Yeah.
Yeah. So all that stuff is smart. It really is. It's smart. It's smart to do it. Save money. We all spend money. There's waste money-wise in our lives if we really look close enough. There's ways of saving money.
Oh yeah. You can do about it. You can do a lot of things for free if you want to, but you won't be comfortable if you did it that way,
Yeah. Okay. Let's take number 6. Number 6 and 7 are good to look at because you can solve 6 easily, and then 7 you got to go back to 6 and get some information to solve 7. So that's one that would be a help to everybody to do. So I'm shooting at everybody getting this and getting it, and it not taking a long time to get it. So we're putting it in turbo, sort of,
Yeah.
So here, I'm looking at the end of the semester, and it ain't going to be long from now. But you got the digestive stuff and get it in you good in short amount of time. So number 6 says that we got a toaster. Got a toaster here. I'm gonna put some loaf bread there.
Yeah.
Got some whole wheat loaf bread there. And it's rated at 1,000 watts. You know what heater elements is used everywhere in our life. You think about it. You got toasters. You have your
dryer.
Your range. Your stove top. You got the oven. Man,
Your dryer.
Man, the hair dryer. Everywhere you look. What'd you say, Roger?
Even light bulbs put off heat.
Man, everywhere you look, you got heater elements everywhere. So.
Old heater that you keep up under your blanket in the wintertime.
The negative blanket, yes, sir. So for here.
Got that.
we want to know how much current would it draw in amps.
You can take the watts and divide it by the volts.
Right. And what do you come up with?
8.3.
8.33333.
So that will be the amps. Now, number 7 says the toaster in this problem with the same heater element. Here, you got a heater element in there. Let's say I got 120 volt. We're going in and we got a heater element. We're going back out here to neutral. The same heater element. Is connected to a 240 volt. Now we're gonna change over to 240 volt. Now don't do this at home. Don't do it at home. You're probably gonna have go kablooey and smoke, and you might be calling the fire department. You might be running out of your house, or you've got a fire extinguisher. So don't do this at home. Over in Europe, I think that it's common over there for like 240 things. So their appliances are going to be different. They're going to be different. It's not going to be the same. Different plug, different heater elements going to be different.
Yeah, I've heard them talk about stuff like stuff goes quick over there, it charges or does stuff faster because it's all 240, you know.
Yeah. Okay, so the question would be now is if you switch over now and you connect it to 240 volt, if you could do it without damaging it. The question would be the power in watts. If we had this new voltage here now, so it's not going to be 1,000 watts. The wattage consumption is going to go up. Okay.
Mm-hmm.
So what you can use to calculate with is when they say it's the same heater element, then the thing that they're counting on being the same would be the resistance of the element, the resistance, which it didn't tell you what that was, but you can calculate it from the first problem.
You got volts and amps, so you can get.
Here's what you got to keep together. You got to keep two pieces of information together. You got to keep 120 volt and 1,000 watt together. Okay, you cannot separate those. You can't separate.
It would be
14.4.
What now?
14.4.
No, it'd be E squared divided by P, I think.
I was talking about getting the resistance for the thing.
Yeah, the first thing you want would be the resistance in ohms.
So that'd be 120 volts divided by the amps, which was 8.33, and I got 14.4.
And that's correct. So the heater element has 14.4 ohms, and they're saying that essentially that the resistance will stay the same even when you double the voltage. It may change a little bit, but it won't change much. Just for this purpose, we're going to say it's going to stay the same. So that's the one factor that you can get from this to use with the new voltage. You can use 240 volt and 14.4 ohms, and it's going to let you calculate a new wattage. So if you go back to your pie chart, which formula can you use that says volts and it says ohms and it'll give you P?
It'd be E squared over
E
R.
squared divided by R.
Right. So
I got 4,000.
squared over R.
Mm-hmm.
And so the E would be the 240 squared over R, which would be the 14.4 ohms.
Yeah,
That's going to give you
4,000.
4,000 watts. Now it sounds like a really serious jump when you double the voltage. Actually, the wattage is quadrupling.
Mm-hmm.
And it sounds unreasonable, but that really is the way it works. It really is the way it works. I'll show you an example. I've got a heater element right here, and just to show you the stampings on something that comes from the store. You see, y'all see that right there? It says 240 volt, 3,500 watts at 240 volt. Y'all see that?
Mm-hmm.
Now watch this. When I flip that same one around, it says how many watts at 208 volt.
240. Oh, at 2,400.
250.
2,500.
Yeah.
Yeah, 2,500.
2,500 watts at 208 volt. Now look, 208 happens to be, that will be the lowest voltage you would have at a house. That's what we have in our shop here. We don't have 240 or 230, we got 208. And that's what's coming in from outdoors from the power company on the transformer. And I don't know why we get 208, but at my house, I'm getting close to 250, but it's a 240 rating at my house. Here, it's 208. So 2,500 watts at 208. You flip the same thing around and look at it. It jumps 1,000 watts just by going up just a few volts up to 240 volts. See that?
Yeah.
You reckon it could be to save money with the power bill?
I guess it could be, but I've always wanted to ask somebody with the power company, why is it that this, why do some buildings get 208, some buildings get 220, some 230, some 240? And I do know that it has to do with the output of the transformer that's outside the building. However, it's equal with the taps on there. They got tap steps on them, and that determines what you get coming into the building based on what tap you go to.
Mm-hmm.
But for some reason, I never remembered to ask somebody like a lineman when I see them around. I never remember to ask them. I need to find out. Maybe Google or whatever. I'm sure there's got to be a reason.
I got a quick question.
Mm-hmm.
Is there a way to figure out, like, with the voltage, what size breaker or whatever it's connected to or coming from?
All right, say that again.
Like, say you had 208, like, is there any way to tell what kind of breaker it's coming from, or do you just have to memorize that?
You mean a breaker like in your house?
Yeah.
The breaker size is going to be, that's going to be based on whoever planned that circuit out. In other words, in a breaker panel, you can have, say at your house, you can have 15 amp breakers, 20 amp, 30 amp, so on. If it's going to be, say, for receptacles, if it's going to be for receptacles, it's going to be either a 15 amp breaker or a 20 amp breaker. Now, if it's a 15 amp breaker, you're allowed by code to have up to 10 receptacles.
Yeah, I know.
So, and then you're going to use number 14 wire. So it really boils down to the contractor or the homeowner that says that per breaker, I want to have 15 amp breakers and do no more than 10 receptacles. Or if it's more of a commercial type place, you might go with a 20 amp breaker and 13 receptacles. You can do 13 receptacles if it's a 20 amp breaker.
So in other words, it's something you got to memorize. Gotcha.
Well, it's actually it's a formula. It's actually in our electrical book for ELC 113.
Okay.
The residential book that you took with me, it's in there.
I'll go back and look at that sometime then.
It is the recommended number for a circuit. If you step up and do a 20 amp receptacle circuit, you can do 13 receptacles, and it has to be a 20 amp breaker, and you use number 12 wire. But that stuff come out of the residential book.
Gotcha.
Now let's say if you step up and do, say, a water heater, then you're talking, you want to go to the nameplate on the water heater, and you want to pick a breaker that's at least that big, and you probably would go up maybe to the next one. It'd be probably like a 30 amp breaker for a water heater.
And then you
That's
use like
sure.
10 gauge wire for that?
10 gauge wire. You go back to the wire chart that I gave y'all, and the wire chart will tell you that for 30 amp, you got to have number 10 wire. And it would be a 30 amp breaker with number 10 wire for say, a water heater.
Gotcha.
You wouldn't know by the voltage what size breaker. That's all based on the amount of load
Gotcha.
you're going to put. The amount of load you're going to put. You pick a breaker based on the amount of load you're going to put on it.
Mm-hmm.
And of course, then you match up the wire size too. You know, say if it's a range, a stove, it may be 50 amp. You know, and so you got to have a 50 amp breaker. If it's a heat pump outside, it may be a 70 amp breaker. Okay, could be a 70 amp breaker for a heat pump for heat strips. I think ours is a 70 amp breaker for heat strips outside for heat
Gotcha.
pump. So you look at number one, you look at the load. And then you pick the breaker and wire based on the load itself. Kind of a rule of thumb, it's best to plan not to use them no more than 80% of the load of a breaker. So if you got a 20 amp breaker, you better don't plan on using no more than 80% of it, because if you stay running right at close to 20 all the time, you're probably going to have some nuisance tripping going on that's unwanted and unnecessary. So plan your circuits to be, 80% or less of the rating of the breaker, and you have some margin in there for heat, and it won't be tripping all the time. So,
Gotcha.
okay. So we finished that one. That I think you'll be good to go now. Honestly, those are the ones that would have been more of a curveball for you. That's my main concern, is that the day that we covered the different types of problems, yeah, you'll be fine. You'll be fine with the rest of the worksheet, honestly. The only other tricky one in there would be, say, number 13. If you look at number 13, it's got, and we don't really have to do the whole thing, but I can, it's actually worth looking at, because it may cause some people to hang up. It probably will. So we got about 5 minutes. I'll get you started on this one, and I think it will help you. So for number 13, actually number 13, 14, and 15 on the worksheet are using the same circuit. So we have a we have an I total of 9 amps. We have R1 is 10 ohms. We have R2 is 6 ohms. And we have R3 is 3 ohms. And R4 is unknown as far as the resistance, but they're telling you that you've got 7 amps flowing out there in that branch. So this branch here, you have this is in series. You've got a series here, and you've got one by itself, but this is in parallel with that series set. So these are in parallel, and then that combination is in series with that. So that's considered to be a combination series parallel that would have been covered in chapter 5. We skipped 5, but we're going to cover it now, and it's not hard. But for the sake of time, it's best to jump onto this now. So the question for 13, it says, find the power at R3. So we want to find power in watts for R3. For R3 only. Okay, so you can take some things and make a quick deduction here if you watch. Let's just give you a clue here. You got a total of 9 amps, right?
Mm-hmm.
And you got 7 amps over here, right?
That
Yeah.
means it decreases by about
What
2
does that
amps.
mean? How many amps has to be flowing here just by a quick look?
2.
It has to be 2. It's going to be 2, okay? So if you say 2 amps here, then you've already got something here to work with here to get watts, right? Just that fast. It looks pretty intimidating, but you've been given enough clues to where you can actually start chipping away at it easily. Okay, so you can take this and this, and you know that by that, you know the formula you're going to use, right? To get the wattage for this one. This one is in a pie chart, right?
Mm-hmm.
Which formula would it be?
Hold on one second. It would be
I squared times R.
I squared times R, yeah.
R, exactly. And the I would be 2 squared times R, which would be 3 ohms.
Mm-hmm.
Okay.
12.
So it'd be 12, yeah.
Be 12 watts.
Mm-hmm.
Look, I want you to show your formula. Type your formulas in that box. I want to actually see your work. Don't just put numbers in. I've got to see the formula, okay? And you need to see the formulas. Don't just do it in your head. You know, do the formulas, type them in. And so that would be for number 13. Number 14 says, for this circuit, find the total power. Total power. Total power. Which means they want the wattage of this one, and that one all combined. They combine. So you want total. So it'll take a couple of steps to do that. So, which how do we begin? How do we begin that process? Not hard at all. Actually, got the current flow, everything right. Got the current flow for everything. You can figure these really easily. This one here's going to take a little something else.
Figure out the volts that's running through the 2 resistors right there in parallel.
Exactly. Very sharp. Basically, that's the answer. For this one, if you figure the voltage drop across both of them together and use it for this, that voltage and that will give you the wattage of that one.
Yeah.
Yeah, everybody follow?
Mm-hmm.
What's up, man? Long time no see. What you doing?
About to say hi to you.
You did? Yeah. Give you yeah.
Doing all right?
Hanging in there, man.
Good, man.
One day at a time, bud.
Anybody else here?
He's the only one. I'm doing Zoom right now. I'm doing the Zoom session. I'm recording. And we're Thursday is technically our Zoom day. It's a hybrid class. So Tuesday they're here. Thursday it's Zoom, or I tell them you can come in and do lab, and I'm going to do a floating Zoom, you know.
Technology, man.
Yeah, yeah.
Man, I didn't mean to interrupt you. I was just passing by.
Yeah. Are you taking classes now or not? No, you're done. Yeah.
I'm so busy.
Right.
I'm over every facility in North Carolina.
Really?
I'm in Smithfield now, so
what position?
project manager.
Good.
Yeah,
That's
I
good.
got 6 plants.
6 plants.
Yeah, 6 plants I'm responsible for. I got 3 people working for me.
Rob graduated from this program.
Yeah.
So are you over electrical projects too?
Everything capital. Every
Everything.
capital project we got.
Every capital project, which means over a certain amount of money.
Yeah, anything over $50,000.
Right.
Yeah, that's almost everything. So
That's all.
anyway, man, I appreciate you.
Yeah.
I'll talk to that girl.
Great,
Good
man.
luck, buddy.
Great. Hold on. Hello? Yeah, that's what anyhow. Now, real quick, guys. Sorry about that.
It's all right.
You know you got what 12 watts here, right?
Yes, sir.
you got the amps and the resistance. You've got the amps here. If it's 9 amps that gets up to here, you know you got 9 here, right? So you can figure that one. And then what you just said, Brandon, was you calculate the total voltage drop across both of these, and you got to add them up, right?
Yes, sir.
Then that voltage drop from here to here is going to be what's here, and that will give you the wattage over there. So that should be a home run for you.
Yep.
You basically add up the individual wattages, and then that's going to give you total watts. And then number 15 asked you, what's the power taken by R4? And you've already answered that in number 14 by what we just said there.
Yes, sir.
So you should be good to go. So anyway, thank you very much for watching. Y'all have have a blessed weekend. This is Durwood King, the master instructor, the nutty professor, or whatever you want to call me. So thank you for joining. We try to make it as entertaining as possible. And so we have we're gonna feature Nicholas here. Nicholas was our one in-person person here. So let's give a hand for Nicholas here. He was here. Yeah. All right. Y'all have a good weekend. Thanks for coming.
All right, you too.
All right. We can always try.
Yeah. So anyhow, any questions?
Not really.
Good. If you do, you can contact me. In any way you need to over the weekend's fine. You can text, call. I'm fine with a phone call. Roger knows that. Roger called me Saturday night about 8 o'clock sometimes, and we'll just shoot the breeze. So talk.
Yeah.
I'm fine with a phone call on the weekend. That don't bother me honestly. And if I'm eating a plate of fish now, then I'll have to call you back after I get done with it. I ain't gonna let the fish.
That's why you text first. I almost made that mistake.
That's right. Yeah, because I'm saying if I'm throwing down on some fish, it's gonna get eat first, and then I'll call you. So.
Priorities.
Yeah. Well, I appreciate y'all joining and everybody watching too. Make sure to make a priority this weekend to. We have to have homework. I mean, this is a hybrid class, so there has to be homework. There's not time to do all this stuff here. There's no way to do it all. If you do worksheets when you're here, you're not going to get your labs done. So make that sacrifice. It's well worth doing. It is well worth doing. Every bit of effort you put into this and all your time is going to pay you back. So when you get your certificate or degree, and later when you get that job, and this is going to be your dividends is going to be a higher pay scale that you're going to get into by what you know with this. And it'll pay you back the rest of your life. I mean, it's paying me back. I mean, I got my degree in '86 from out here, 1986. And, I spent 22 years doing it in plants, and I've been out here teaching for 10. So you've made a good move to get the skill sets. Just keep learning. Learn all you can. Get all the electrical you can. Get all the mechanical you can. Get all of this entire program, industrial systems. And be multi-craft. That's really where it's at in this county, is being a multi-craft technician. And you will normally have work. It would be very rare for you not to have work. Especially nowadays with the economy picked up the way it has in the last few years, there's maintenance managers calling me pretty regularly looking for people. So yeah. I mean, I can help connect you with a plant, and you've actually got kind of a choice, kind of which way you want to go. Food processing, you're going to make more money. If you go in manufacturing around here, it's not quite as much money, but cleaner environment. You can go to work with a contractor doing construction type electrical if you want to travel some. So there's you got a lot of options. Solar field is another one opening up that you can. We got some solar classes coming up next semester. That in the electrical degree, that's another thing. I have one graduate, Dwayne Waters, that's doing solar field work now. So he travels wiring up, installing solar panels in these fields.
Are you going to be teaching that class?
No, Carla's teaching solar. She's teaching that one.
Is it going to be?
There's so many new classes coming up. There's no way for me to do it all. There's just no way.
Yeah, I understand.
So that got her involved in it. And I'm teaching the industrial classes in that new degree. Carla's doing the solar, which there's 2 solar classes, and then Jake's doing the commercial end, and he's doing the electric code specific classes. So he's more on the commercial end, and he's on HVAC, heating and air. Carla is bridging between residential wiring and solar and AutoCAD. And then I'm doing the industrial control end of it that goes into that degree. So it's taken 3 of us to get that degree to put it together. So there's a lot in it. So it's a good degree. If you want to specialize in electrical, go for it. It's a good thing. So yeah. Well, y'all have a nice weekend. Have a blessed weekend. Thanks for joining. And I'm gonna go ahead and click stop so it can process, and then I'll upload. And thank y'all, and you have a blessed weekend.
All right, Durwood. See you.
Thank you. Thank you for joining.
Later.
And for anybody watching that's not connected with our college, my name is Durwood King. I'm an instructor here at Sampson Community College. You can contact me by email at dking@sampsoncc.edu. And I'll be glad to give you information about our different programs. We have an industrial systems degree that's multi-craft. That's got electrical, mechanical, hydraulic, pneumatic, gearboxes, conveyors. It's got machine shop in it, got some refrigeration, got a little bit of welding in it. So it's got a little bit of everything. It's got a new electrical degree that's strictly electrical, but it includes residential, commercial, solar, and industrial electrical control classes and national electric code. So it's a really packed degree just for electrical. It's electrical systems technology. And then we have the HVAC program. If you want to get involved in heating and air, we got a brand new whole degree for that. And, and we have other things. We got a welding degree out here. We got all kinds of stuff. We got certificates. So if you want to come just for a year and get a certificate, you can get a specialized electrical certificate. That's only 4 classes. You can get it in a year. You can get a industrial maintenance certificate in about a year. So you can, and then there's a diploma. So there's, you can get other things if you don't have to, if you can't come full time for 2 years, you can get a certificate. Or if you got, say, 4 to 5 years to stretch it out, you can get a degree in that amount of time if you go part-time. So anyway, you can drop me a line, and be glad to give you information and get you signed in and get you some skill to help get you in a better position with your job. So thank you for watching, and y'all, God bless you. Have a nice weekend.